so last time we embarked on our quest of understanding the Ramsey numbers R3K. And the first thing we did is show sort of a general upper bound for the Ramsey numbers RLK, and this resulted in an upper bound of k squared in this case. And then we showed, using a vertex deletion method, that a lower bound of the form k to the 1 minus, whoa, 2/3 minus little o 1. What am I saying? 3/2. Sorry, it was the independence number is 2/3. OK. Minus little o 1. And I just ended the last class by discussing how to improve this to a bound of the form k squared over log k squared using an edge deletion method. So there were some, so I'll just quickly remind ourselves of that idea. So for a lower bound, you want to construct a coloring. And for us, we discussed it's enough to construct a graph. So I'm just focusing on, say, on the blue graph, and put with the following properties. So we want to find a graph G on n vertices, which is triangle free. And has independence number at most n to the 1/2 times log n. I don't really care about these constants so much in this class, but I'll just put a constant here for some c. And if we can construct such a graph, then this implies that the Ramsey number R3K is at least k squared over log k squared for some constant c. OK? For sufficiently large c. And just to remind heuristically where we were, so we wanted so the idea was sample G from G and P, where P will be some about 1 over root n. So I'll give it a name here. So it's some gamma over root n, gamma small constant. We'll see in the paper what just some stupid number that comes out. And what will we do? Then we'll define a new graph G primed to be G minus an edge from every triangle. So here, I'm going to be a little bit tricky about. So actually, it turns out here any maximal subgraph will work. But we're going to be a little bit more clever about how we choose this maximal subgraph. And it will make our lives a lot easier. So just a definition is that a collection of actually, maybe I wouldn't even define it here. Sorry. We'll just say minus some graph, which is a maximal collection of edge disjoint triangles. So I'll just write it here. So what's the picture? First, I sample my G. It's going to have a bunch of triangles in it. I mean, we can check from our formula yesterday, there'll be quite a few triangles. And what I'm going to do is I'm going to take a maximal collection. So just keep adding triangles until any further triangle will share an edge with one of these triangles. So, OK, so say this is a maximal collection. Now I can't add this. Now, when I take and I remove all of these edges, then I better have hit every triangle. The remaining graph better be triangle-free, right? Otherwise, I would have found a triangle not in this not in this collection, and therefore contradicting the maximality. So note, G prime is triangle-free. By definition. Okay. So I should say, I mentioned yesterday that this proof is originally due to Erdős from the 60s, but this proof I'll follow is actually due to someone who's here, which is Michael Krivellevich. Okay. And really actually introduces some nice ideas that we'll see echoed in the last couple lectures of the course. Okay, good. So now I need to do a couple things to understand this graph. And perhaps the hardest thing here is to calculate the independence number. In fact, that's really the only thing I need to do here. And it's a little bit hard because I can't directly put my hands on the probability that a set is independent because I now modified it in this slightly confusing way. But there's actually a really nice trick in order to study this complicated object. Actually, by the way, just to remind you, please ask questions. Shout if you have any question. You don't need to ask me for. So yeah, this part of the row can ask one question this lecture. Okay, so I'm going to work towards understanding the independence number in this graph in two steps, right? And we'll ultimately show this for my modified graph G prime. So, okay, so this lemma, well, I'll just write it and then say something about it. So let P be much bigger than 1 over n, say bounded away from a half, and let K be bigger than, I'll put it big in the middle here, bigger than some large constant times log n over P. So this is a familiar number from yesterday, so we'll come back to it in a second. Then, sorry, and I'll say let, I forgot to say G is G and P. Then every subset of size K induces at least P times K squared over some constant, 16 edges. Okay, so this is sort of a companion to the result that we proved the other day on the independence number. So I want something a little bit more robust. What did I say yesterday is every set of size bigger than some number like this in G and P is not independent. So I always know that there's one edge in here. This is just a slightly stronger version saying that the number of edges in here is like what you'd expect on average, P squared over P times K squared over 2. Okay, and then I throw in a little constant because I don't, so within constant factor of average. So I actually get a nice constant fraction of the edges. This has size K. And intuitively, this makes a lot of sense. We're going to need lots of edges in every one of these near independent sets, because when you come with your big, scary triangle factor and remove it, you don't want to kill my independent set. Okay. So the proof is very simple. I'm not going to do it. I'll just say one word. So union bound over all sets of size K, just as we did yesterday. But now instead of having this 1 minus P to the K choose 2 factor, because there's no edges, now I just need a slightly more, I'm just asking what's a binomial random variable has at most this many edges. It's almost the same calculation, but you get some funny constants floating around, so you can still do the union bound, done. You have constants to play with. Okay, maybe that's all I want to say about the proof. I do encourage you to do it as an exercise, as it's useful to get used to the numbers. Okay, so the second lemma is actually also due to someone in this room, and Erdős. So, and also a very useful result. So this is due to Erdős and Teteli. This is Prasad Teteli, who proved the following kind of, like, we'll see it's actually quite simple, but perhaps surprising at first. Simple to prove, but lovely. Okay, so so I'm given some family F. And these are going to be events in a probability space. Of course, we'll never need to really be this general. You can just imagine them as some events in our probability space G and P, which is exactly how we'll apply it. Okay, and let epsilon t. Okay, so this is a bit of an interesting definition here. Oh, I should have said for some t. For some integer t, let epsilon t be the event that t independent events. So among these AI, all occur. Then we can bound the probability of this interesting event here by the following. So this is 1 over t factorial times the sum of the expected number of the events in my collection to occur to the t. Okay, so every time, I feel like even when I say this, I get a little bit confused by this event. The thing to have in your mind, the picture to have in your mind is as follows. Right, so imagine I have some events, which I'm going to draw as dots here. And I'm just going to say that these are an independent collection, right? So these are all independent as a collection. And I'm going to draw like a tuple here for all of these. Okay, they're not the same size. But for all tuples of these t independent events. This event here is just the event that one of these edges is completely filled, all these events occur. Okay, that's it. Great. So it's a lovely thing to prove, so let's just do it here. I'll leave that for a second. Okay, so whenever I get confused by proving some inequality between probabilities, sometimes it's useful to write them down just as some sort of, sorry, yeah. Sorry? What was the second word? Mutually dependent. Yeah. So yeah, completely independent, I guess. So we'll see exactly what we use, but the probability of the intersection is the product of the probabilities of the individual events. Yeah.
I guess here you need bound to the finite because the expression still makes sense with an infinite family, right? Do you need the family to be finite?
Let's see.
Because
Don't see. I don't know. We can look at the proof in 1 second and see. For us, like we don't even know about infinity in this time in this lecture series. But I would suspect it's also okay. There might be some funny thing when there's something's infinity, like expectation. But, well, we'll see right here. So I think it should be fine. Okay, so let me just write down the indicator. It's not strictly necessary step. So the indicator of the event t is at most. Okay, so now maybe it's useful to find the following definition. So this is kind of the picture that I had on the board. So this will be all tuples, ai1 up to ait, such that that collection is all independent, right? This, whatever the word is. So I should say in f to the t, and these guys are independent. And now I claim the following thing. So this is ai1 up to ait in I. I did the right thing. Yeah, all good. Thank you. Good. And now I claim that this is an inequality. Why? Because if this thing lights up, right, there's going to be something here in I that's going to light up. And now I count all permutations. So I get t factorial here divided by t. Oh, good. OK, so trivial. I'll put a tick like that. OK, now let's just take expectations of this guy. OK, good news. That's the right-hand side. Right, so now I'm going to use this property of independence here. So this is going to be, it's going to factorize. OK. And now let me just keep adding events, right, until I get all pairs. So this I claim is just at most, or adding terms, I should say. And that's the proof. Sorry, this is for all I. I guess I didn't give an index for that number. Good. Now, I kind of wanted to leave both of these on the board, but maybe not. So OK, so now I claim that we can really make this plan go through. We take our random graph, we sample, we remove these edges, and it doesn't hurt the independence number too much. So let's prove it. OK, so just to remind you, we sampled G from G and P. Oh, I realized there was a little typo in what I did. Oh, no, it was fine. I wrote P. OK, all good. G and P, where P is going to be my gamma over root n, and gamma will be some small constant. And just remember that this G tilde is, I know this is a bit of a glary zone of the board, but there you go. Just delete some maximal edge disjoint collection of triangles. OK. Now, I'm going to let, oh, sorry, and just as useful at this point, let's write K, this is my potential independent set size, to be C, where C is some constant I chose before, times n log n. Right, and this just agrees with this. This is just log n over p, like constant log n over p. So it agrees exactly with what we've seen before. Now I forget what to do. OK, so now let's call it maybe Q be the event. So I called it Q because it's like a quasi-randomness event. So the event that every K set induces at least this pk squared over 16 edges. Okay, and we know that this holds with high probability. That's why I'm allowed to call it a quasi-randomness event, I guess. And let's just note we can basically assume this in our calculation. So the probability that G tilde, oops, forgot to write independence number. So what's my goal in life? To prove that this is a low probability event. But what I'd like to do is show right away that I can intersect with this event. Well, that's easy. Just this probability is the intersection with this and the intersection of the complement, but the complement has probability little o1. So this is alpha g, blah, 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 intersection q. In fact, I'll just write less than or equal to plus the probability that q, didn't write a script q, sorry. The probability q's fails, but this is going to 0. So if I want to show this goes to 0, I just need to deal with this. Let's go here. And again, we'll just do this by a union bound. So this actually, this is a very common thing that you'll see is like, when you want to go to do a big union bound over a lot of events, in some sense, you need to say something that like much, much rarer events, because the probability of an event is fighting against the number of such events. But here, we don't have that. So this q is just little o1. So it's very important that I intersected with q before I take this union bound, so I don't have to sum up this little o1 for every independent set. Okay, so it's sort of obvious from this point of view, but it's a useful thing to have in your mind. Okay, so now, let's union bound this guy. So of course, this probability on the right-hand side is just that there exists I independent in G and Q. And now I'm going to just union bound over all Q. Over all I, rather. So this is G primed. Did I call it primed or tilde? Tilde, sorry. I called it primed before. Okay, I independent in Q. Oh my God. G tilde and Q. Good. So this is over all potential independent sets. And of course, just by symmetry, all of these guys are the same. Right? Every independent set just looks completely symmetrical from this point of view. So this is just equal to n choose k times I independent in G tilde and Q. Okay, so now we have to deal with this confusing event. So here I've just fixed some I. If you like, it could be 1 up to k or something. Okay? Yeah, exists in I, so union bound. Yeah, thanks. Okay, so here we go. Here's my I, a fixed I, and I want to know if it's independent. I want to calculate this probability. Now, I has size at least k over here, and I know that in G, I'm going to have lots of edges in here, right? Because I've intersected with this Q event. So this has pk squared over blah, blah, blah edges. So what did that mean? If this is independent, this triangle factor had to come in, or a collection of edge disjoint triangles, and hit each one of these edges, which seems like kind of a crazy event, and indeed it is. We're going to use this Aristotle to prove that that's very unlikely. Okay, so to prepare for that, let Ti be the collection of K3s, sort of just in the complete graph. So before you percolated everything, just consider all triangles that have one vertex out. These are kind of the offending guys. sorry, there could also be guys here as well. So with at least two, I'll just say at least one edge in E. Okay, at least one edge in I squared. Okay, and what are my events? They're quite natural now. Let A sub I be the event that this triangle, TI, was contained in your random sample G. Okay. Okay, so what have I done? Here's my I. And I'm considering all possible triangles here in my unpercolated graph, so the complete graph, that intersect this I and could potentially zap an edge in my independent set. And AI, of course, is just the event that the ith one of these triangles is included into G. Now, notice that, and here's like the magic moment, is that if the triangles that I remove are all edge disjoint. So that means these are all independent events, right? Two edge disjoint triangles. So in order for this to be independent, you had to come in with at least this many triangles, edge disjoint triangles, and hit some edges in here. And we can use Erdős-Teteli to say that this is very unlikely. So this is the magic moment. So I mean, as I said, you can do it without this idea, but it's substantially more technical. So so let's go. So let T be. Okay, so how many triangles do I at least need to see? I'm actually just realizing you do potentially have these triangles inside of here. So I could let's just lose a factor of 3. Doesn't matter anyway. So this is P times K squared times whatever, some number. Good. And note by this lovely Erdős-Teteli lemma that, okay, the event that we're interested in, maybe I'll call this star. Let's call this thing star. I feel like my shoe. Okay. This is at most the probability that E of t holds, which is at most 1 over t factorial times this business. Okay, whoops. What am I even doing? Great. Okay, so what is this? This is just the expected number of triangles that meet I. Okay, this is just some easy business to compute. So how many triangles meet I? Well, I have to choose at least 2 endpoints, meet I in an edge. So I have to choose at least 2 endpoints inside of I. Okay, then one endpoint in who knows where. And they all have to be included like this. Okay. Maybe someone has a question while I tie my shoe. Yeah, so this collection of AIs here is all possible triangles that meet I. So they could intersect, but the special sauce is we're only interested in a bunch of triangles occurring that are all pairwise disjoint, because that's exactly this Maxwell collection of disjoint triangles. So it exactly falls into this setting here. Okay, so now it's just a matter of computing to the finish. So Okay, so what is 1 over t factorial? I can just pull it inside here. Is there more questions? Unhappiness? Happiness. It's, I thought you were okay with your unhappiness, which is fair. Okay, so okay, so this is something like this, being slightly, yeah, there's a, okay, so now I have to remember what t is, so it's this pk squared over, okay, some number. Oh, sorry, no, wrong. Yeah, sorry, 3. There's a gamma that's coming anyway, so we're all good. Sorry, pk squared, all good. Very good, very good. Sorry, now we can cross things out. This is p squared. This probably doesn't look good on the board. Okay, so I kind of don't want to just put it there. Okay, maybe I can fit. So there's some confusing constant here from these. There's a p squared now. So what is p? It's 1 over root n times, okay, there's this gamma, but the root n is exactly canceling with this n, which makes sense if you think about it. And what's left is this constant just times a gamma squared. Okay, times some business upstairs. So some constant p k squared. I think that's correct. Good. And now all we need to check is that it beats this guy over here. So this is done, so I can erase this. Okay, so, and choose k times the probability, this business here, independent in g tilde and q, is at most en over k to the k times this, which is basically gamma cube pk squared. I'll just pull a k out for now. Like this. Good. Right. So now, just to remind you, so k, k was like some large constant over gamma times log n. Right. And of course, p is, as you remember, like this. Oh, sorry, I also forgot. Times root n. Okay, so this p times k is going to be, in this exponent, like some large constant times log n. So this is like some large polynomial factor now. This k over n is just giving like a root, but now this is killing this. In fact, it doesn't even, I actually didn't even need that part, because I'm being so lazy with constants. So this is whatever, some n to the minus c to the k, which goes to 0. Okay, and this is the proof. Okay, is there any questions at this point? So let me make a few remarks about this proofs. So just to remind you, we ultimately showed this lower bound, okay, which is a result of Erdős. You can actually get the same thing using the Lovász-Loka lemma. So I'm not going to talk, if I had a bit more time in this course, I would talk about it, but I won't talk about it, but some of you will know. Remark. Same bound as possible. And I mention it here because it's nice to note that these things sort of fit into the same sort of space of techniques. Here we're sort of almost seeing the Lovász-Local lemma work like in context. And we actually introduce some ideas that are useful later as well. Any more questions? I'll just erase the boards now. Maybe there's some jokes while I erase the boards. Okay, so what I'd like to talk about, okay, so what do we know so far? We know this bound of k squared over log k squared, and we know an upper bound of k squared. What I'd like to talk is a little bit about the upper bound. This is actually interesting. I want to talk about it not just because it corresponds to R3K, but when you start thinking about the upper bound, it also helps you start thinking about what's happening for the lower bound. So it's almost like the lower bound and the upper bound are cousins of each other, as we'll see. So we'll actually set us up to prove Kim's theorem and get rid of this extra log factor. Okay, so upper bounds on R3K. Okay, so what I'd like to hopefully prove today, maybe stretching a little bit into next time, is that R3K, well, this is a theorem due to Aitai, Komlos, and Samotij. From the 80s. And in fact, I'll state a slightly stronger form due to Shearer, who just improved the constant. I think this is like 83 or something. I lost my whoops. So they proved R3K is at most 1 plus little o1, quantity going to 0 as k tends to infinity, k squared over log k. And they did this, and in particular, I'll write the stronger theorem due to Shearer. But Aitai Komlos proved the same thing with the worst constant. The following bound, general bound for triangle-free graphs, independence number and triangle-free graphs, which, as we already know, we're already used to the idea that this is the whole game for R3K. What's going on with these independence number and triangle-free graphs? So let G be a triangle-free graph on n vertices. With average degree d, then alpha of g is bigger than 1 plus little o1 n over d log d. So here I have to be a little bit careful. This little o1 here is actually going to 0 as d tends to infinity, not as n tends to infinity. So but this makes sense for us because, of course, we're interested in graphs that typically have degree around square root n. So that's really the interest here. So here, little o1 tends to 0 as d tends to infinity. All right. Good. Okay, so I'd like to So it's something slightly annoying about teaching this, which is in a class, what you'd like to do is give a proof that gives the most amount of intuition and like the most amount that sort of seems the best motivated, but you also want to give a very short proof that you can actually fit into the class. And I find Shearer is a bit hard because I mean, there's essentially two proofs of Shearer. Both of them are kind of a bit magical in both ways, and so therefore seem a little bit mysterious. But at the same time, it's actually an extremely natural bound to get. And you bump into exactly this behavior everywhere. So what I'd like to do is actually do something a bit funny, is I'm going to sketch a proof of Shearer, but it's not the proof that I'll give. So I'll sketch a proof of sort of a nibble type when I'm doing sort of Shearer in rounds, but then I'll actually give Shearer's original proof, which is a very delicate proof, also a nibble. I'm just removing a random vertex at a time and very carefully tracking what's going on. Okay, I believe with the sketch that I'll give is also can be made into a proof, but there's a few technicalities that I don't want to bore you with. But let me make a few remarks before I get there. So this constant here, this 1 plus little o1, is actually, it's a bit of a mystery. So it's not so hard to show. And I'll put this on into the problem set, that if you take an appropriate random graph, we can get an upper bound of like this. So take whatever, D regular random graph, or just take some random graph with the appropriate edge density. You can essentially show that this holds. So what's the right answer? We have a 2, we have a 1. And this is actually a genuine mystery. And while it might just seem like a constant, I think there's a lot of really interesting mathematics that lives between these two things. So at this point, even just improving a 1 plus epsilon for a fixed epsilon here, it would be a major deal. So improving Shearer. So I suppose most people believe that maybe something like this is the truth, but it's really not known. Improving Shearer by a 1 plus C factor is a major open problem. Or just anything shedding more light on what this particular factor of 2, this factor of 2 really comes up in sort of a lot of places. Okay, so now let's sketch the proof of Shearer. Sketch of a proof of Shearer, not necessarily our proof. It's not Shearer's proof, actually, either. Okay. But I think it's really maybe how you should think about what's going on. Okay, so you give me this graph. I said average degree D, but you're not nice people. Let's just say maximum degree D for now. Okay. Here's my graph that you gave me. Every vertex has max degree D. Okay. Now, I'd like to start by building some kind of independent set. So this is going to be like a nibble-like argument for those of you have seen this idea before. Maybe I'll use a different color. So what I'd like to do is first choose some set I1 just randomly with some probability P. So randomly with probability P. Okay. I want this to be an independent set. When is this going to be roughly an independent set? Actually, does anyone have a guess? For what P? Just roughly an independent set. Someone in the 5th row, maybe? Not Oliver. So if P is like gamma again will just be some small constant for us, over D, I claim that I is going to be very close to an independent set. Why? So I'm a vertex. I have D neighbors. each one of those is included with probability much smaller than 1 over d. So the expected number of my neighbors that are in is less than 1. So what does that mean? When I take my first nibble, here's my I1, the expected degree of this graph here is going to be like 1. Expected average degree is like 1. And so it's close enough that you can obviously just clean it up. Let's just for now pretend it's genuinely an independent set. Okay, so this is my nibble, my first nibble, and it has size p, which I'll actually call p1, times the size of the graph. Okay? So I put this in, and now I need to delete, if this is going to be my independent set, I need to delete everything that has a neighbor into here, right? Almost every vertex has all of its neighbors out by this same calculation. So that means this set here is d times bigger than this set. So this set has size gamma d times n. This world here will be of size about gamma n. Okay? And I'm just going to rip that all out. Great. And now what I'd like to do is just keep iterating this strategy. What's the magic calculation? Or it's not magic, really. I think it's actually very intuitive. About why we can keep going. So to answer this, I asked 2 questions. The first is just what's the probability that a vertex survives into here? OK, I've already kind of told you the answer, but I want to do it again. So what's the probability some vertex, any vertex, survives into round 2? In other words, it lives here. Okay. Well, the picture is easy. Here is my vertex. Oops, I called it V. It has d neighbors. The probability that it survives is that none of these guys are included. Also this guy, but OK, whatever. So this is about 1 minus p to the power of d, or d plus 1, or whatever. OK, so here's the second important question. What's the probability an edge survives? OK, and here is where the rubber starts hitting the road. So here's the picture for this. Here's my edge xy. What's the probability it survives? Well, it survives if both of the endpoints survive. So I have to look at the neighbors of this and the neighbors of this. And because it's triangle free, these 2 sets are disjoint. So the probability here is 2d. OK, minus 1 because of the edge in between, but whatever. OK, it's basically 2d. Maybe I'll go back to my convention. That will save me from the lawyers. OK. Now what I'd like to do is ask, OK, so I ripped out this big piece here. What I'd like to say is that this graph is much like the original graph, except the degree is smaller. In particular, I'd like to say this set kind of just looks like a random set that I ripped out, meaning that the proportion of neighbors that lie in here is going to be like gamma times d. And the number of neighbors that survive is like 1 minus gamma times d. So I'm sort of deflated the entire graph in this natural way. So what I'm going to do is just, since I'm not really proving anything, I'm just arguing for you. I just want to calculate the average degree in the remaining graph. Well, I know how to do that because I know the probability a vertex survives. So I know the average number of vertices. I know the probability an edge survives. So I can get some idea of what the average degree is. So the average degree is 2 times the number of edges of this graph, which I have not given a name, but I'll maybe call it just d2, divided by the number of vertices in G2. And I know this to be just heuristically to be 2 times the number of edges in the original graph times 1 minus p to the 2d divided by the number of vertices in the original graph, which is 1 minus p to the d times n. Okay. So what is this? This here is just the average degree in the original graph times 1 minus p to the d. Okay. Now, right, so and this, what is this quantity? P I chose to be gamma over d. And so this whole quantity is something like 1 d times 1 minus gamma. Okay. And now we can immediately see why we can continue. So this, I've sort of verified that this picture is in some sense correct. But now I'm going to choose my P2, so I'm going to take my second nibble. P2 is going to be what? It's going to be some small constant, not times this initial degree, but times a new degree, which is 1 minus gamma times d. So I've been able to push up. I get this factor. I can choose a larger set with a larger density in this set. How big is the whole set that I choose? What's the size of my I2? Right, so that was the density I chose it, but I only chose it in this part of the world, but that was 1 minus gamma proportion of the world. So I2 is 1 minus gamma times n times P2, and now this gamma will cancel with this one. So this is, oh my god, gamma over nd. And the point is here is that in the second round, you chose exactly the same amount as you chose in the first round. So that's great. So I did something, basically didn't change anything as far as I care about it, and I can do it again. So I can keep doing this until I run out of space, and that's my independent set. Just take the union of all these independent sets, and I'm done. So the only thing to check here is when do I run out of space? So when does this or process or procedure stop? Well, in each step, I shrink the graph by a 1 minus gamma factor, right? Every time I'm going down it by a factor of 1 minus gamma. So let's say t is the point that I stop. And this will be the size of the graph when I stop. Okay. Now, if the size of the graph is smaller than the total number of vertices I would like to include, then I'm pretty much toast. There's nothing I can do. So I'm basically done when this is like gamma n over d. Okay, so the n's cancel. N's cancel. D, this gamma is just some small constant. This is just, this gamma is some small constant. So if you want to solve for this, you get t. So this is going to be t is going to be like 1 over gamma, right? So that's about when this is constant. But you can go a log d further because of this. So this is log d. Okay, and now at last we can understand where the shearer number comes from, right? I took a bunch of nibbles, t nibbles of size gamma n over d. So my total independent set is just the product of those things, which is 1 over gamma log d, which is exactly what we wanted. Okay. Okay, so there was a few places that I cheated here. In particular, In particular, it's not so clear why this is true. So it was true sort of one vertex at a time, one edge at a time, but what if I'm not exactly regular? So maybe my initial graph you gave me was regular, but now I take a big bite out of it. Now there's some vertices a little higher, a little lower, so you have to do something about that. So here you can use some sort of convexity, or you can use some kind of correction, but you have to do something. But this is really the correct story for what's happening. Okay. Now I have just a very awkward amount of time left, because I would like to put, okay, let me just state the result I would like to prove, and then I can quite quickly finish it. So okay, so here comes the slightly magic bit, is Shearer analyzes this argument not when you're doing a little nibble at a time, but when you're removing a vertex at a time. And when you're doing something so subtle, you really need to make sure the numbers add up correctly. So it's basically just an induction, is what Shearer's doing. But you have to be a little bit careful. And I find that this amount of carefulness abstracts from the main idea, which is really big, bold, and true. So here, you'll see what I mean. Let f of d equal d times log d minus d plus 1 divided by d minus 1 squared. So the theorem that Shearer actually proves is that G n vertex triangle free and average degree D, there is, then the independence number is at least this confusing function. Okay, which is basically log d over d for d tending to infinity. He has something very special because and the point, because you really need to do things carefully, and the point is that this f is a special function that satisfies this particular differential equation, which sounds complicated, but it's all very just simple bookkeeping. So this is d times d plus 1 is equal to 1 plus d minus d squared. So f satisfies this differential equation. And basically what you can do is use just Taylor's theorem. So if I vary the density by a little bit, so this is some d primed very close to d, then I can write it, as a lower bound plus d prime minus d times f0. So for any, let's maybe say bigger than 0, just because. Then we just have this just by Taylor's theorem. And the fact this function is nicely convex. So you just use the remainder version of Taylor's theorem. The next term in it is always positive, and then you delete it. Okay, so I was hoping just to prove it, but I'm now just out of time. So I'll pick up next class, and I'll just show that what we can do is just take our graph, take a random vertex, remove it, and we'll see that when we delete x and its neighbor, so it's just like a nibble of size 1, and apply induction to the rest, we actually can just apply, we can also just like bootstrap this upward to get this theorem. Okay, so I write it out in case you want to try to prove it at home. I've told you everything you need to do, but I'll quickly finish it off next time, which is not tomorrow, but Thursday. And then we'll get on to talking about triangle-free process and upper bounds. Sorry, lower bounds, the sharp lower bounds for R3K. OK, thank you very much.